All right, so we have seen how you handle a single stereocenter within a molecule. But as it turns out, our molecules will sometimes contain more than one stereocenter. So let's look at this. So here is a slightly longer molecule, slightly longer chain. And it has some groups on the chain. And if you notice, we have 2 carbons that are sp3 hybridized and have 4 different groups on them. These are going to be stereocenters, and therefore they're going to potentially have the R or S configuration. And correction, they will have either R or S configuration. So to do a lot of times stereocenters, there's simply a matter of looking for in your molecule and finding carbons that have 4 different substituents. And that's really all there is to it. It's fairly straightforward. And once you train your eyes to look for that, you'll find it fairly quickly and easily. Now, so here's a molecule. We've already learned about enantiomers. So we can talk about enantiomers in a second, but as a start, let's look at these molecules and assign their configurations. So what we did was we said for the Kohn-Ingle-Prelog convention, what we want to do is we have 4 different groups. This carbon, and I'm kind of putting a dot on right now, that carbon has an oxygen, a carbon, and a hydrogen. Well, the hydrogen is going to be the low priority group, lowest atomic number. The oxygen is going to be number 1 because it has a higher atomic number than either of the carbons. But which of these carbons has a higher priority? So let's draw this molecule out again and show what we look at. So this carbon, there are 2 carbons. You might say, well, that's sort of a tie. Well, it's not a perfect tie because this carbon has 3 hydrogens attached to it. This particular carbon has a carbon that's attached to another carbon, and we're going to put these in order of atomic number. This carbon has another carbon and 2 hydrogens. So as it turns out, the carbon on the right is higher priority because we see a carbon with another carbon rather than a carbon with just hydrogens. So this carbon beats that hydrogen, and that carbon's higher priority. Now it's not above the oxygen, but it's going to be number 2 priority. And so we'd say 1 to 2 to 3 on that carbon. This is that's clockwise. This is going to be the R configuration. We can do the same over here with this chlorine. That chlorine is going to be 1, the hydrogen is going to be 4. As it turns out, this carbon is again going to be 2, and the carbon on the end is going to be 3 for the same reason that we talked to at the bottom of the slide. And this is going to be 1, 2, 3. That's now counterclockwise. This is going to be S. Great, we can assign these configurations. Now, you might wonder, how do we draw the enantiomer? Well, the hard way is what we've already done. The hard way is to simply try to draw the mirror image of this molecule. So this carbon with the chlorine is going to be closer. And further away is going to be the carbon that bears the oxygen. And if you go through the process of assigning the stereochemical configurations, it looks like we've drawn the same thing. We haven't. This is now R, and this is now S. So we can manually think of the mirror image, and the mirror image will have the opposite configurations, and these are now mirror images. They are non-superimposable. So these are indeed enantiomers. And in practice, when you have enantiomers, you will reverse all, this is what I should underline, all of the stereocenters. So if you have 1 stereocenter, you'll reverse that 1 stereocenter. If you have 2 stereocenters, as with this molecule, our R and S become S and R. S for the oxygen, R for the oxygen over here. So these have swapped. They've reversed. So anytime you reverse all your stereocenters, you will get an enantiomer. Whether it's 1 stereocenter, 2 stereocenters, 16 stereocenters, reverse them all, and you will go to an enantiomer.